This is Lab 5, Faraday's Law, by Saban Patel. The purpose of this lab is to A. Observe and collect data on the interaction between a conductive tube of aluminum foil and a magnet falling inside of it. B. Create a computational model of this interaction using VPython, also Glowscript. And finally, to compare the computational model to the observed data. Some important concepts used were Faraday's law, which can be explained by the change in magnetic flux induces an EMF in a loop, and if that loop is conductive, a current will be induced. Lenz's law, the magnetic field generated from an induced current is in the opposite direction of the change in the flux. Third, Biot-Savart law, and finally, Newton's second law. Some important formulas used were Faraday's law and the formula for the EMF of a moving dipole. Other formulas were also used, such as formulas in Newton's second law, but I did not list them as important. The experimental procedure was to first measure the length, width, and radius of the aluminum foil tube with measuring the inside and the total radius of the foil. 2. Determine which end of the magnet is north using the magnetometer app and marking it. 3. Position the aluminum foil tube so that it fits in the frame of the phone recording. 4. We drop the magnet to the tube and record it. 5. We scrub the video and determine the exact time codes, or the closest we can time codes from when the magnet entered the tube and when the magnet exited. Finally, we repeat steps 3 to 6 5 times and find the average. Some assumptions and observations. We cannot use a ferrous tube since they contain iron, and there would be a magnetic interaction in which the magnet sticks to the tube rather than fall through. Also, the magnet falling through the tube will fall slower than simply dropping it from the air because as flux increases through the tube with the magnet dropping, it creates an electric current opposite of the falling magnet, which in turn creates an induced magnetic field that pulls the magnet upward, which therefore causes it to slow down. The measurements of the aluminum foil were as follows. The length was 0.33 meters, the width was 0.01 meters, the inner radius of the aluminum foil was 0.015 meters, total radius 0.026 meters, and then the mass of the magnet was 24.1, and the magnetic dipole was 2.18. The average time of the magnet entering and then exiting the tube was about 3.12 seconds. The Glowscript code is shown. The red is where we establish the physical constants used in the computational model. The blue defines the geometry of the tube of the aluminum foil. And finally, the green is the function to calculate the magnetic field of the bar magnet. This red box is the function to find the change in magnetic flux with respect to time, also called d flux d time, or the rate of change in flux. Here you can see the loop that was given to us through the starter code. This contains the loop, the calculation of the current, and the calculations for the forces acting on the magnet. Finally, it uses Newton's second law to update the position of the magnet in timed intervals for the graph. It goes from top to bottom in the order of the red to the blue to the green. The results show the magnet dropping through the tube and the velocity versus time graph of the magnet falling through the tube, with the computational simulation giving us a time of 3.301 seconds and the experimental average being 3.12 seconds. Interpreting the computational simulation. Because the north part of the magnet was pointed down, and because of the increase in magnetic flux as the magnet went down, we can deduce that the induced current is in the counterclockwise direction. Therefore, we can also deduce that the blue current, which is the induced current, is in the counterclockwise direction, and the red is in the clockwise direction. Also, if the magnet is flipped with the south end being on the bottom, the velocity and positions of the magnet would still remain the same due to the new induced current being in the clockwise direction. Here, we interpret the slope of the velocity versus time graph. When the slope of the graph is negative, the net force on the magnet is that of gravity. But when the slope is 0, the net force on the magnet is 0, because the upward force is due to the aluminum foil tube and the gravity cancel each other out. Therefore, the velocity will remain the same. While the results of the experiment were similar, the results of the experiment could have been more accurate. But because we are performing in a home environment, they were not as accurate as it could be. We could improve them by performing the experiment in a controlled environment, such as a laboratory, far from any metals. Also, by having a better method to capture the exact times the magnet entered and exited the tube. Finally, what if questions. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamic of the falling magnet change? First, the induced magnet would be greater, causing the upward force to be greater as well. Therefore, the time it takes for the magnet to entirely fall through the tube would also be greater. What if the next question, what if the holes or slots were cut into the tube? How would this affect the ring currents in your model? This would mean that there's less loop areas for the magnetic field, therefore causing less magnetic flux. That, in turn, would cause the magnet to fall faster than without any holes or slots. That was my presentation. Thank you.